Okay, so the last chapter that we have is about the so-called thermochemistry. So when we did the definition of chemistry at the beginning of this summer session, we define chemistry as the study of matter and the changes that it undergo. Now, usually in the changes that it undergo, you always have the so-called energy. Okay, and in most chemical reaction, the energy is in the form of what we call heat. So when we're talking about thermochemistry, these are just the energy accompanying changes in chemical reaction. Okay, so the main field that you have here is the so-called thermodynamics. So if you're going to look at this, this is the science of the relationship between heat and the other forms of energy. But if you're going to look at this one, thermodynamics, so dynamics is just changes, energy changes. So what are these energy that you have? But the one that we're going to focus on is the field of thermochemistry. So this is an area of thermodynamics that concerns the study of the heat absorbed or evolved by a chemical reaction. So it's just the energy that accompanies chemical chains. Okay? So since this is the study of the energy that involves chemical change, so we have to know what is energy. Okay? So energy, this is just the potential or capacity to move matter. And if we're going to look at the different forms of energy, we could put it electromagnetic, mechanical, electrical, or chemical. Okay? And this form of energy, they can be converted from one form to another. Okay? So you always see energy around us. If there's what we call burning of fuel, okay, this is an example of what? Heat evolving reaction. Okay? So when you see some fuel being burned, usually, okay, it produces energy. Now, if we're going to look at the main focus of what energy is, we need to look at this term here. Okay, these are just forms. Okay, but if we're going to look at the energy as it is, so we either have a kinetic energy or what we call the energy in motion. So this is the energy associated with an object by a virtue of its motion, and the equation associated with this is this one. Kinetic energy is equals to 1/2 times mass times velocity squared. Okay? So if you're going to look at the energy, what can you say about this so-called energy? Is energy a material? Most likely it's not. Energy is not a material thing, but a property of matter. So exists in different forms that can be what we call converted from one form to another. So if we're going to look at the unit of energy, this is not new to you. Okay, what we have is the joule. So joule is kilogram times meter squared over second squared. So that's the SI unit. Okay, but the one that is commonly used is the so-called calorie. Okay, so calorie was originally defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree. Now, if we want to look at what's the equivalent of calorie in joule, So 1 calorie, you have 4.184 joules. Okay, so that's the exact, we could say, conversion factor. Now, for the sake of doing problem solving using this equation, kinetic energy is equals to 1/2 of mass times b squared. So we can have this problem: a person weighing 75 kilograms or 165 pounds runs a course at 178 meters per squared, meters per second, or 4 miles per hour. So what is the person's kinetic energy? So if you're going to look at this one, all we need to do is what? Replace whatever we have here. So we have 75 kilogram, and then you have 1.78 meters per second. So if you're going to look at the unit, you will end up with this, which is the same as joules. Okay? So if you're going to do the calculation, I think you're going to get around 119. If you're going to do the calculations, it's 1.78 squared times 75 divided by 2. You will get around 118 point, like this. But there's three significant figures here. Three significant figures. So you're going to write this in three significant figures. So that's, we could say, the basic calculations that we have here, but we're going to focus more on other types of calculations. Okay? Now, if we have an energy in motion, we also have an energy in position. And that's potential energy. The energy of an object by virtue of its position in a field of force such as gravitational, electric, or magnetic field. And if you're going to look at the equation of potential energy, you have here mass times gravitational constant and height. Okay? And if you're going to look at the unit here, if you're going to do an operation here, you still end up with this one, which again is equals to joules. Okay? So those are the basic thing, kinetic energy and potential energy. Now, how about internal energy? Okay? So internal energy is just the sum of the kinetic energy and potential energies of particles making up a substance. And if you're going to look at the total energy, it's just the sum of everything. Okay? Now, how are we going to look at this so-called internal energy? So try to imagine you have water in a dam. So what can you say about water? It has kinetic energy and potential energy. Now, what else do you see in water? Water is made up of what? They're made up of molecules, which is further made up of smaller particles like electrons in a nuclei. Okay? So when you look at this one, okay, you got to include this in the so-called total energy. So it has the kinetic and the potential energy, and the other materials that made it up. That's what we call your internal energy. So overall, if you're going to look at the amount of energy that water in the dam has, okay, It's not only the kinetic and the potential energy, but the internal energy that you have there. The energies that make up the substance. Okay? So that's what we call your internal energy. Because if you're going to look at the law of conservation of energy, what does it says? Energy may be converted from one form to another, but total quantity remains constant. So the classic example, the ball on a hill. So usually if it's in position, what energy that it has? You have the potential energy, right? Now once it starts to move, that potential energy is converted to kinetic energy. And when it stops, its energy is now the potential energy. But the ball itself, it has its own internal energy. Okay? So this is the only one that converts from one form to another, but the total quantity would always remains the same. Okay? Now, what other stuff that you need to know in a thermodynamic system? So you have here what we call a system and a surroundings. So usually they said in thermodynamics, it's just the exchange of energy between a system and a surrounding. Okay? So a system is the one that we study. That's the substance under study in which a change occurs. Is called the system. So this is the one that we're interested. Now, the surrounding is everything else in the vicinity. Now, if you combine the two, what do you call this? The system and the surrounding. Anyone? The system and the surroundings made up the universe. Okay? So usually what we're going to look at is the system. How the system and the surroundings interact with one another. Okay? You can have an open system, a closed system, or an isolated system. So what's the difference between the three? An open system is you can have an exchange between matter and energy. Okay? A closed system, energy is the only one that can interact. An isolated system is there's no interaction between matter and energy. Okay? So an open system we could say is the surroundings around us, everything that you can see around us. A closed system is one wherein there's only interaction between the energy. Okay? An isolated system is just a material that is on its own. Like if you have, I'm not sure, a system where your water remains hot or cold after some times. Okay? A doer plus or a thermos. So that is an isolated system. And everything is something to do on how these two interact. Okay? Now, usually when we see energy interact between the system and the surroundings, the energy is in the form of heat. But that's not the only form of energy. Okay? Heat is just one form of energy in a chemical system. Okay? So heat can be described as the energy that flows into or out of a given system. Why? Because of temperature differences. Okay? So usually heat would flow from a warm object to a cold object. And maybe that's the reason why it's called heat, right? Because I don't think you're going to call something that comes from a cold object to a warm object heat. Maybe you can call it coldness, but there's no such thing as that. Okay? Heat is the one that flows from a hot object to a cold object. Okay? There's no such thing as coldness. Anything that comes from a warm object to a cold object is heat. Okay? And if you're going to look at this, we put the symbol small q. It is positive when heat is absorbed by the system or you add heat to the system. So if you're going to look at this, heat goes to the system. That's a Q plus, or Q is equals to plus sign. And Q is defined as negative if heat is evolved by a system. So that's when you have heat going out of the system. I hope you remember that, because that's one of the common concept that you should know at least in this chapter. Okay, the concept of heat, because what happened is most of the question or some of the question in this chapter are true or false question. Okay, so I want you at least to understand the concept, especially this thing about when is q positive and when is q negative sign. Okay, now you can associate your heat with the heat of reaction, because as I have told you, we're talking about energy that is involved during chemical reaction. Okay, so when we're talking about heat of a reaction, this is just the value of Q required to return a system to the given temperature at the completion of the reaction at the given temperature. And there's a term that they use for this, what we call heat of reaction. Okay, so this is the endothermic and exothermic process. So how are you going to remember them? Okay, look at the first two letters. So endothermic, a chemical reaction or process in which heat is absorbed by the system. So Q is positive. Okay, so how are you going to remember this one? Heat enter the system. That's endo. Now, exothermic process, on the other hand, this is the chemical reaction or process in which heat is evolved by the system. Q is negative. So this reaction vessel, the reaction vessel will feel warm. So what will happen? Okay, heat exit the system. So when the surroundings get hot, so that means the system release energy to the surroundings. So that's an exothermic reaction. When the surrounding gets cold, that means the heat enter the system. It leaves the surroundings, making the surroundings cold or cool. Okay? So the thing that you need to remember in an endothermic reaction, the reaction vessel cool, heat is absorbed, energy is added to the system, and Q is positive. In an exothermic reaction, the reaction vessel warms, heat is evolved, and energy is subtracted from the system, and Q will be negative. Now there is a quantity, or we could say term, that is associated with this one. And we call it the enthalpy. Okay? So enthalpy is what we call the term that we use to describe an extensive property of a substance that can be used to obtain the heat that is absorbed or evolved in a chemical reaction. Now, it is an extensive property. What does it mean? It depends on the amount of the substance. So if you have more substance, your enthalpy is bigger. If you have less substance, your enthalpy is smaller. If you still recall what extensive property is, it depends on the amount. Okay? So a 1 gram substance will what? Have lower enthalpy compared to a 1 kilogram substance. Okay? So most of the stuff that we have here is a little bit abstract. When I say abstract, it's hard to what we call describes them. Okay? Now, in addition to that, we can also say that enthalpy is a state function. So when we're talking about the state function, it's a property of a system that depends only on its present state, which is determined by variables such as temperature, pressure, and it's independent of the history of the system. Okay? So, state function depends on present state of a system and not on the path by which the system arrived on that what we call state. So, for instance, this one. The altitude of a campsite is a state function. So it's just this. It should be straight line. I really have a hard time. Maybe I'll try to make it like that one. Okay. So whether you take this pathway here, you take this pathway here, what you do is just, it depends only on the present state. It doesn't what we call take into consideration how you arrive to that campsite. Okay. Now, aside from enthalpy, your internal energy is also a state function. So it's just looking at the present state, not on how the system arrived on that state. Okay. So if we are an in-person class, we could say what is important is we are in a classroom at Pace University. In what ways you arrive in that classroom, it's not important. Whether you arrive by subway, by driving a car, by a cab, by walking, okay, or by swimming, it doesn't take into consideration that thing. What it does is just look at the present state. Okay? It is independent of the path taken to reach it. That's what it means by a state function. Now, since enthalpy is associated as an external energy that describes the heat that you have, the substance that can be used to heat, to obtain the heat, okay, we can also use it in terms of a reaction. So the change in enthalpy for a reaction at a given pressure, temperature and pressure. And you're going to use the delta sign, which is change in enthalpy, and it's just equals to the difference of the enthalpy of the products minus the total enthalpy of the reactant. And if you're going to look at the enthalpy change here in terms of what we call the heat of reaction, that's just equals to the heat of reaction at constant pressure. So it just equals to whatever heat your system or your reaction has as long as the pressure is the same. So what does this mean? Okay? So if you're going to look at it, so this is the reaction of how you produce NaOH and hydrogen from sodium metal and water. So if you're going to look at the energy that you have here, so this is the energy of your reactants. So what can you say about the energy of the reactants? Okay, it's higher compared to the uh, what we call enthalpy, not energy, enthalpy. I think that's the term that we have here. So what we're going to do is we're going to look at the difference. So based on the thing here, okay, the products that you have there would be what? Okay, the products would have less enthalpy compared to the reactant. And if you're going to look at the delta H there that you have, this is the reaction or the equation that we have. So what does this mean? Since this one is less than that one, you will have a negative delta H. And you can associate this one with the Q or the energy that you have. Okay? Since the heat that you have here is more compared to the reactant. So that means your Q will be also negative. Now, the question that I'll ask now, is this an exo or an endothermic reaction? Anyone? You can type your answer in the chat box. Is it an endo or an exo? Okay, so this is an exo. Okay, because the energy is released. It says there, heat is released. Now, we can expand, or we can at least expand the concept of enthalpy with internal energy. Because right now, we're just looking at enthalpy with regards to heat. Okay? So how are we going to relate enthalpy with the internal energy? So if we're going to look at the definition that we have here, we can have this relationship. So enthalpy, that's H, this is internal energy, and this is pressure times volume. Okay? But if you're going to look at this one, this is heat, this is the internal energy, and this is work. So if you're going to look at this, many reaction takes place at constant pressure. Okay, so the change in enthalpy can be given by the following. So what happens if it's a constant pressure? So remember, delta H is equals to Q of P. Okay, so you have a constant pressure there. You can put this as delta H. Now, constant pressure, so that means the pressure is not changing. The only one that's changing here is the volume and the internal energy. Now, you rearrange this one, you can have this thing. But if you're going to simplify this one, this is energy, this is Q, and this is just W. Or you could just put this plus here, plus W, and depending on what will be the sign of the delta B here, can make it a minus W or a plus W. Because the term that we have here, the negative P times delta B, that's the energy needed to change volume against the atmospheric pressure, and it's called work. Okay? So let's try to look at some system and see where these terms came into place. So the reaction that we have, sodium reacting with water to produce NaOH and H2. What do we say about the Q? It's negative. Now, how are we going to determine the W? Okay, so if you're going to look at the W, you just need to look at the delta B. And delta B is just equals to what? The final volume minus the initial volume. So what do you think is the value of delta B? Will it be positive or negative based on this illustration? Anyone? Will the delta B value positive or negative? Okay, so as you could see here, this is the initial volume that you have, and then by the end of the reaction, the volume is higher than that one, so that means this is a positive. So P times a positive here, what will be the value that you will get? Negative times positive, you have a negative value. So what does this mean? Okay, the hydrogen that formed there did the work to raise the piston, and for that there's a corresponding work of around 2.5 kilojoules, aside from the heat that evolved. Okay, now the question here now, how much energy does the system has? So you have here 368.6, and you have here minus 2.5 kilojoules. So overall, you will have 368.6 minus 2.5, an energy that is around 366.1 kilojoules negative. So this is now the combinations of your heat and work. Okay. So energy is equals to Q plus W, similar to this one. Now, how are we going to relate it in a given reaction? Whenever we have an equation and we write the energy associated with the given equation, we call it a thermochemical equation. Okay? As of now, you already know how to write this, what we call balanced chemical equation. Okay? So if we're going to what we call, just look at the energy associated with the chemical equation, we call it a thermochemical equation. Now, usually, that value corresponds to the moles given in the equation. So, how you're going to interpret this one? Okay, this is the amount of energy that you need to react 2 moles of Na with 2 moles of water to produce 2 moles of NaOH and 1 mole of hydrogen. Or you could say this is the energy that you need to produce 1 mole of hydrogen in the given reaction. Or this is the amount of energy that you need to react 2 moles of sodium metal. That's what makes it an extensive property. Because you change the value that you have here, you're going to change the amount of energy or enthalpy that you have here. So this is just exclusive for what? Whatever's the number of moles that you have in a given reaction. It says here, the thermochemical equation is the chemical equation for the reaction, including the phase label, in which the equation is given in a molar interpretation. And usually the enthalpy of the reaction for these molar amounts is written directly after the equation. So let's try to look at this for you to understand how you solve thermochemical equation. So I have a problem here, similar to the one that we have in the what we call recorded slides from last fall semester. So sulfur burns in air to produce sulfur dioxide. So the reaction produced 9.31 kilojoules of heat per gram of sulfur at constant pressure. Now you are asked to write the thermochemical equation for this reaction. Okay, so what are we going to do? So you have there a sulfur. So what do you need for it to be what we call burn? You need an oxygen, right? So sulfur plus oxygen, it will give you sulfur dioxide. Uh, so from it alone, you could see here 8 sulfur, 1 sulfur, so maybe you can put this as 8. And once you have here, you're going to have 8O2, so you can just put here 8O2. So we could say this is the balance equation. But the one that's being asked is the thermochemical equation. So what information do we have here? 9.31 kilojoules of heat per gram of sulfur. Okay, so we could say 9.31 kilojoules per gram. We can also put the word the negative sign. Why? Because of this word, evolves. When you have evolves, release, okay? So that means the energy leaves the system. But if you have the words absorb, enter, then you're going to have a positive sign for that. Okay? Now, what else did we need to do? This is gram, so we need to find the molar mass of sulfur. So this is just around 256.56 grams of sulfur per 1 mole of sulfur. So it's just 8 times whatever is the molar mass of sulfur. Right? So 256.56, that would be 32.07 times 8. You need the periodic table for that. And once you have it, you cancel out the grams. So this is the amount of sulfur. 256.6 times 9.31. So you're going to get around negative 2.39 times 10 to the 1, 2, 3 kilojoules. So you can write it like this one. So for every 1 mole of sulfur that you burn, there's a corresponding 2.39 times 10 to the negative 3 kilojoules of energy that is being released. Again, the sign here telling you that it's going to be an exothermic reaction. Okay? Now, how about if you're asked to do other calculations similar to this that involves manipulation? When you manipulate a thermochemical equation, this happens when the equation is multiplied by a factor. The value of the delta H by being multiplied by the same factor. When a chemical reaction is reversed, the sign of delta H is also what we call reverse. Okay? So what does this mean? So let's say this is what the thermochemical equation for 1 mole of sulfur means. Now, what if we are asked to write the thermochemical equation for the dissociation of 1 mole of sulfur dioxide? So how are we going to do this? How are we going to do this, what we call modification? So we are asked how much amount of energy that you have here to dissociate it. Okay? So for this, what we're going to do is we reverse the reaction. And if we reverse the reaction, what happened to our delta H? The sign is reversed. But are we done? Because the ones being asked is 1 mole. So what do we need to do? We divide everyone by 8. So this now becomes 1 over 8. And in that case, you're also going to divide this by 8 to give you the thermochemical equation right now, which is equals to what? Delta H is 2.39 exponent by 3 divided by 8. So you will get around 299 kilojoules. And this is having this. So see what happened? When you divide everything by 8, you divide the delta H also by 8. And that's what makes it an extensive property. Okay? So I hope you have followed this type of problem, because you're going to have a calculation problem like this in your chapter quiz and maybe in your final exam. Okay? So the way that you're going to apply stoichiometry here in the heat of the reaction, it's similar to what you did in chapter 4, the grams that you convert to moles. And once you have the moles, it has a corresponding heat of reaction like the one that you have here. So this is for 1 mole of S8. Now, if you want to have 1 mole of SO2, you divide everything by 8. So your delta H will also be divided by that number. Okay? So the starting units grams of A, then you convert it to moles, and then you convert it to kilojoules. Don't worry, we have a sample problem like this one. So you are asking here what would be the equivalent amount of heat, let's say instead of moles, in terms of gram. It's still the main thing that you need here is your thermochemical equation. Without the thermochemical equation, you cannot solve the problem. So all you're being asked here, what is the equivalent mass if you burn 15 grams? Okay, what is not the mass? What is the equivalent heat or energy if you burn 15 grams? Now this one, this is the equivalent energy if you burn 1 mole. So you can do a ratio and proportion on this one, but we just follow the dimensional analysis that we have been doing since the beginning of this session of this course. So all you need to do is just what? Convert the 15 grams into, if you want to get the corresponding energy associated with that mass. So 15 grams, you multiply it with, for every 1 mole, you have the 256.56 grams. Is that what we have earlier? Just want to make sure. Yeah, 56.56 of S8. And then for every 1 mole of S8, you have negative 2.39 times 10 to the 3. And if we're going to solve this one, 15 divided by 256.56 times negative 2.39 exponent negative 3, or not, exponent 3. So I have here around 139.7, or 140 kilojoules, or we could say 1.40 times 10 to the 2 kilojoules. Analyze. If you have question, you can ask. We can try this one, where the daily energy requirement for a 20-year-old man weighing 67 grams is this amount, and for 20-year-old women weighing 58 kilograms, the daily requirement is this amount. Now, if this energy were to be provided by the combustion of glucose, how many grams of glucose would have to be consumed by the men and women per day? And for the reaction of glucose, this is the amount of energy that is produced. So how are we going to what we call determine this thing? Now this is the other way around, because the one that's being asked here, how much of glucose you need to supply the energy needs. So one that needs this amount of energy and one that needs this amount of energy. So we can start. I'm trying to put this a whiteboard. So the one that we have for the mass of the glucose, so there's two reaction or calculation here. So we start with the guy. So this is the amount of energy. And for every 1 mole of glucose, this is the amount that it provides. And then we could say, for every 1 mole of glucose, this is the mass. So that is equals to what? 1.3 exponent 4 divided by 2.82 exponent 3 times 180.2. So you will have around 831 grams of glucose. Now for the other one, the energy requirement is just 8.8 times 10 to the 3 kilojoules. And then for every 1 moles of glucose, 2.82 times 10 to the 3 kilojoules. Okay, so try to do the calculation itself. Okay, and then times 180.2 grams glucose per 1 mole of glucose. So 8.8 exponent negative exponent 3 divided by 2.82 exponent 3 times 180.2. So you're going to need around 562 grams of glucose. Or we could just say this is what, an 8.3 times 10 to the 2, and this is 5.6 times 10 to the 2 grams. So that's how you're going to solve problems like this. So what can you say? Now you may ask yourself, how were they able to determine these values that they have here? Or how do they measure the heats of the reaction? Which is a valid question. Okay? So we will first look at the heat needed to raise the temperature of a substance, because this is the basis of our measurements of heat of reaction. So we have some terms associated with it. Heat capacity, molar heat capacity, or specific heat capacity, or just specific heat. Okay? So when you say heat capacity of a substance, it's the quantity of heat needed to raise the temperature of a sample of a substance by 1 degree Celsius. Now, if you're going to look at the associated unit to it, if it's 1 mole of a substance, you call it the molar heat capacity. If it's 1 gram of a substance, you call it specific heat. Okay? So heat capacity, this is the amount of heat needed to raise the temperature of a sample of a substance. Now, if it's in terms of 1 mole, you call it molar heat capacity. If it's 1 gram, you call it specific heat capacity, or just specific heat. Okay, now you can ask yourself, how were they able to determine this? The heat required can be found by using this equation. So if it's heat capacity, you will see it's just C times delta T. C is your heat capacity. Okay? When it is a specific heat, so you have there an S times the mass. Now you might say, where did they get the values for this heat capacity? They have an instrument that's called calorimeter. Uh, since we didn't do experiment 9, that's the experiment 9 is all about. You have what we call the copy cup calorimeter on it. So the calorimeter is just a device used to measure the heat that was absorbed or evolved during a physical or chemical reaction. So this is a simple coffee cup calorimeter. You just have two styrofoam cup in place of on top of one another. So what you do there is you mix something. You'll be able to determine the changes in heat that we can correlate to changes in energy. Well, if it's a calorimeter, the what we call bomb calorimeter, so you put the reaction inside it and you see determine the changes that it has. So that's how they were able to get this heat associated in a given reaction. Okay, that's the direct way, but there will also be an indirect way to get it later on. Okay, so aside from thermochemical equation problem, you will have we could say heat capacity or specific heat problem in your quiz. And all you need to know is this one. And as usual, I'm going to give you the equation. You don't need to memorize anything. Okay? So you're asked here, a piece of zinc weighing 53.5 grams was heated from 20 degrees Celsius to 28 degrees Celsius. So how much heat was required? The specific heat of zinc is 0.388 joules per gram per centigrade or Celsius. So this is the one that you can determine from the calorimeter. So how are we going to solve this one? So we use the equation that we have here, this one. Q specific heat times mass times delta T. Specific heat is 0.388 joules grams centigrade. Mass is given here as 35.8. And the delta T is 28 minus 20. So when we're talking about delta T, that's final temperature minus initial temperature. So all you need to do is just do this one. So what do you get? Around 111 joules. So if you see, you cancel out the unit that can be canceled out. Or let's say I make this 50 grams. So I'm just going to replace here this one. So if that is a 50 grams, so what is the thing that we have here? 0.388 times 50 times 8. So this is just around 155. Now you ask yourself, does it make sense that when you increase the amount, the heat that you have also increases? Okay? So when you increase the amount there of your material, the amount that is going to what we call the needed to heat it also increases. Okay? So what is the difference of this with the other one? So from this, you're going to determine the thermochemical equation using the corresponding amount here. So what are you going to do? You're going to determine first how much heat was associated with this mass of nitromethane. And then once you have that, you can determine if I have 1 mole of this, what's the corresponding heat that will be evolved. Okay, so it's similar to what you earlier, to what we did earlier, wherein we have what? Q equals to Sm times delta T. Okay. Now, what is the additional information that you have here? You have here the heat capacity of the calorimeter. Okay. So we can get here, okay, from the Q reaction, I would say I use the heat capacity of the calorimeter. So I'm going to use the C delta T, that one here. So that would put me with 3.044 kilojoules per degree Celsius times the changes that you have, 28.81 minus 22.23, and that will give you 6.58. And then you multiply it with 3.044, so you will have around what, 20.03. So what does this 20.03 represent? And if we're going to look at this, we could say that's the amount that is associated in the calorimeter. Okay, so we could say this is a negative sign. We don't need to do this one, because what do we do? The heat coming from the calorimeter, that is also the heat that you produce in your reaction. So what does this mean? This amount of energy release this heat. This amount of material release this amount of energy. So all you need to do now is maybe convert that to moles. So if I'm going to use some sort of the whiteboard. So that is the amount of energy associated with 1.724 grams of CH3 NO2. And what I'm going to do, I'm going to multiply this with the molar mass, which is 61.04 grams of CH3 NO2 per moles. And what will happen? My grams will become moles. So negative 20.03 divided by 1.724 times 61.04, I will have around 709 kilojoules. So what does this mean? So if I'm going to write the thermochemical equation, I think it's 3 over 4. So this is what you have. I can put this directly here. The delta H is equals to negative 709 kilojoules, because that corresponds to 1 mole of my nitromethane. But I will be going to be a simple specific heat times mass times delta T equals to the heat of the reaction. That's the problem that we will have in the quiz. Okay. Now, as I've told you, if you cannot obtain the heat directly, you can do it indirectly. Okay. So what you do is you use this so-called Hess law of heat summation. That's what we did in, I'm not mistaken, in chapter 9 when we did the getting the formation of your crystals. Okay. So for Hess law of Hess law of heat of summation, for a chemical equation that can be written as a sum of 2 or more steps, the enthalpy change for the overall equation equals the sum of the enthalpy changes for the individual steps. Okay? So supposedly we want to get the heat of the reaction for this. But the problem is we cannot measure it directly. We cannot measure it in the calorimeter. But what we have is a reaction wherein we have this and this one. Okay. In order for those for this to add to give the reaction that we want, we must first multiply the first reaction by 2. And in doing that, what will happen? Okay, we will be able to get the heat of the reaction for the graphite that we have here. So we multiply this by 2. So this one is times 2. And what we have here now, we can cancel this. Okay. To be able to get a reaction like the one that we have. We can cancel one of these. So we end up with this equation. 2C graphite plus oxygen producing 2CO. Now what is the new delta H here now? So we multiply this by 2. So we end up with a negative 353 kilojoules. So that's heat of summation law, Hess law. That's what Hess law is. You just add until you end up with the one that you want. So for instance, this one, how are we going to look at the relationship between heat of fusion and heat of vaporization? So if we're going to have these equations that we have here, okay, so you have H2OS to H2O liquid, and then you have H2O liquid to H2O gas, right? So if you're going to look at this, you can cancel this out. So you end up with H2OS producing H2O gas. And this is your delta sublimation. So this one is your heat of fusion, and this is heat of vaporization. So how are you going to relate the two? So we could say this is just the summation of these two. We add them together, we cancel the one that is common on both sides, so we end up with this relationship. The heat of sublimation is just the sum of the heat of fusion and the heat of vaporization. Another way of looking at this Hess law that we have here is maybe using this reaction here. So how are you going to make these two reactions become that one? So what is the enthalpy of the reaction for the reaction of calcium metal with water? You cannot measure the enthalpy directly, but you have these two reactions. So what you can see here, okay, you look at the two reactions. So which one is in the reactant and which one is in the product. So as you could see here, you don't have an H and an OH in this one. So that means maybe you have to invert it to make it like this. And what will happen to the enthalpy? It will become the opposite sign. And then as you could see here, oh, I have a 2 here. So that means I think I need to multiply this by 2. So that means you have to multiply this by 2. And you don't have this anymore. So once you have that, you can cancel out that is one that is common on both sides. Is there anything common? Okay. So you have this and this. You have this one with this. And then you have calcium here. Okay. You have the hydroxide here. And then this one. Oops. So once you have here, the next thing that you're going to do is the delta H, because that's the one that is being asked. So you have 55.9 times 2 plus negative 543.0, which gives you 431.2 negative. So for that, you might expect a problem or calculation like this type of problem. So you just have to be very careful with the calculations that you have. Okay. Now, in addition to this one, you also have this so-called standard enthalpies of formation. Now, when you have a standard enthalpies of formation, so usually that's the one that has this sign, degree sign. That's different from this one. In one set, in what sense they're different? When you have the degree sign, that means it is in a standard state. Okay. So standard state refers to the condition wherein the standard dynamic conditions chosen for the substance when these things are usually 1 atmosphere pressure and 25 degrees Celsius. The way that you read at them is delta H0, the standard enthalpy of the reaction. And if you have the book, okay, there is a list of it at the end of the book, like a table. Okay. Now, what do you think need to know about this standard enthalpies of formation for elements that exist in more than one physical states? You can have different values. So for instance, you can have different value for oxygen and different value for the ozone. Okay. So carbon can exist as a graphite or as a diamond, and they have different values there for delta H. Oxygen can exist as an oxygen or an ozone. So these are what we call the allotropes. And the reference form is the most stable form of the element. Now, if you're going to look at this standard enthalpy of formation, this is just the enthalpy change for the formation of 1 mole of a substance from its element in the reference form. So you will see here some compound that is formed from the elements. Okay. And the thing that you need to remember, if you have the standard heat of formation for an element in its reference and standard state, is usually 0. So if you're going to look at the example here for the liquid water, the standard enthalpy change for the reaction is this one. They found out that it is equals to what we call negative 285.8. Now, if you're going to look at the values for each of them, you can see it in a table. At the end, there's appendices that gives you the table. But you can use the Hess law to determine the standard enthalpy of formation. Okay. So for instance here, you are asked to get the standard enthalpy of formation for this reaction that we have here. And the way that you're going to do it is you're going to be given a set of reactions. So for instance here, we could put your graphite reacting with 2Cl2 producing CCl4 and a heat of formation of around 135.4 kilojoules. And then you have another set of reaction which is 1/2 of hydrogen plus 1/2 of chlorine producing HCl with heat of formation of around negative 92.3 kilojoules. And then last but not least, you have CH4 producing C graphite and 2 hydrogen with heat of formation that is around plus 74.9. Now the question is now, what are we going to do? The same thing that we do in the Hess law. Whenever we modify the heat of formation, the delta H. So which one do we need to look at it? So maybe this one. You can have this one also. Now for the Cl2, we can have it here. For the CH4, we can have it here. So all we need to do now is modify them or manipulate them to give the one that we need. So what can you say about the CCl4? I think this is fine already. Okay. And if you're going to look at this, what will happen? The graphite here, you have a graphite here, you have a graphite here that can cancel out. And then if you're going to look at the the HCl, you need 4 here and you only have 1 here. So maybe we can multiply this by 4, making this what? 4H2, 4H2. 4 divided by 2, that will give you 2. 4 divided by 2 will give you 2. So this one can be canceled out. So this one is multiplied by 4. So what else? Did we satisfy everything? So this is CH4, CH4, 2Cl2 plus 2Cl2, 4Cl2, and then CCl4, and then that one. And all you need to do now is do the alteration here. So 135.4, that's a negative. And then 4 times negative 92.3. And then plus 74.9. So I get here 429.7. And then we can have another example here. So heat of vaporization of methanol at 25 degrees Celsius and 1 atmosphere. So how are we going to do this? So heat of vaporization. So you have a liquid to gas. Now, in your quiz or exam, you will be given the value. Because if you don't have the value, you cannot also solve the problem. Okay? So what I'm going to do is, I'm going to give you the liquid one is, ayan na, ito naiinis ako eh. Okay? So you have negative 238 kilojoules per mole. For the gaseous, it's negative 200.7 kilojoules per mole. Now the question now is, what is the amount of energy that you need to convert your liquid methanol to gas methanol? So the way that you do here in the heat of the reaction is just the summation of the heat of your products minus the summation of the heat of formation of your reactants. So you have here negative 200.7 minus negative 238.7, and you have what? $38.7. Now ask yourself, does this make sense? Does this make sense that this is a positive? Which, if I ask you, makes the reaction what? Endo or exothermic reaction? So if you're going to look at it, the positive sign means you need energy to make your liquid methanol into gas. So it's an endothermic reaction. So you have to think about those type of what we call problem. Ask yourself, does this make sense? Okay?
Professor,
Or, yep.
can you repeat that, please?
Huh?
About, can you repeat what you just said, please?
So you ask yourself, does the positive sign make sense? Remember, this is the reaction that you have. If you want to vaporize your methanol, do you need heat or do you release heat? Now, liquid methanol to become gas, you're going to need heat. So that means you need an endothermic process. And an endothermic process usually gives you a positive delta H. That's why this value makes sense. Because you're going to need energy to make your liquid methanol into gas. How about this one? So this is the answer that we have from that one. How about this one? You have methyl alcohol. This is toxic. I don't know if you heard the poisoning that happens in the Caribbean of some tourists, and they found out that instead of drinking ethanol, what they are really drinking are methanol, which is toxic. Okay. So you are asked here, calculate the delta H for the following reaction. So how are you going to solve this? So for instance, we have this one. So we put it here, and then water, we put it here, and then the formaldehyde, we put it here. So what do you think the value of oxygen? Anyone? So what is usually the one for elements that is in the more stable form? So that is a zero value here. So what you're going to do, you get the total here, subtract it with the total here. And the answer is your delta H. So if you have it, we can do it this way, 2 times 150.2 plus 2 times negative 285.8 minus 2 times negative 245.9 plus 0. So what do you get? So I have an 87.2 here. No, 2 times negative 150 872 here, and I have 491.8. So when I add them together, negative 872 minus negative, I have a negative 380.2 kilojoules. So what is the reaction? The reaction is exothermic. And I don't know if you're going to believe me, okay? If you are over, what's the age for you drinking? 21. So if you drink, sometimes you feel hot because there's heat that is being released, okay, by your body. So that's the explanation that we have for this one. Now, the last part that we have here, so I mean, when you do the calculation, I want you to double check or triple check your answer because I can assure you in a multiple choice uh, problem, all choices there are the number that will come out if you mess up your calculation. Okay, so I would suggest you double check or triple check calculations that you have. Now, if you're going to look at the application of the concept that we have here, we can use it in terms of what we call the food. We can ask yourself, why do we eat? Okay. One reason why we eat is we need the food to fuel our body. As it says here, there are three needs that is fueled by the food. They supply the substances for growth and repair of the tissue. They supply the substances for the synthesis of compounds used in the regulation processes, and they also supply energy. Okay? And the way that you do this is there's a combustion process when you eat food in our body. And you can look it in terms of this one. And based on this, you could say is between a carbohydrate and a fat, this is the amount of energy that you're going to produce. Now, my question now is, which is more energetic? Maybe I can ask everyone to put their answer. Which do you think is more energetic, the carbohydrates or the fats? Carbohydrates gives you around what? 4 kilocalories per gram, while fats gives you 9 kilocalories per gram. So which do you think is more energetic? Is it the fat or the carbo? So based on this alone, it is the what? The fat. But you always ask yourself, how come people always have fats? Because the explanation there is the main source of energy is what? Provided by the carbohydrates. You will only utilize the fats when all carbohydrates are used up. So that's the only time the fats can be utilized. But if you're going to look at the energy that it's produced, the fats produce more energy compared to the carbohydrates. But that's can only be utilized when there's no more carbohydrate. Okay, that's why the reason that if you don't eat for several days, most likely, okay, you will get thin because during that time, if you don't supply your body with the carbohydrates, the energy would come from your fats. That's the explanation that you have there. Okay, you can only have your fats utilized a source of energy if you don't have the carbohydrates. Okay, now we all know about the energy that we have right now. Okay, you can also what we call correlate it to this chapter. Okay, how the fossil fuels is being utilized as source of energy. Okay, the one that they have about these the so-called fossil fuels. So when we're talking about fossil fuels, we're talking about the oil. So what happened? How did they have this oil? The organic matter was converted by bacterial decay and pressure to petroleum, which is your oil, gas, and the coal. Okay, so the coal is really an issue. There's no such thing as clean coal because what happened? Why is the coal a little bit environmental pollutant? It has sulfur in it. So when you utilize it, you can produce SO2 or SO3. When react with water, can gives you S2O4 or S, H, H2O3, sulfurous and sulfuric acid. Okay, that's why they try to at least minimize the use of this what we call coal as major source of this what we call fuel. And I think that's the end for us. Okay, so this is the end of the chapter. So if you have any question for now with regards to the remaining, we could say requirement, I think that's the best time to ask. Any question? Do you have any question? To the, how many of you here? 7 students that are here. So as I have told you at the beginning, the quizzes are open. The 9 quizzes are open for you to take another crack. So each of you will be allowed to have at most 2 quizzes in each chapter or 2 attempts in each quiz. Yeah, you can email me if you have any question that you cannot remember to ask at this time. Okay. So some of you has already taken the second quiz or the second attempt in this quiz. If you get 100, you don't need to take it. But if you want to prepare for the final exam, it's fine. The deal that I have is whatever is the highest score in the 2 quizzes, that's the one it's going to be recorded. Link to a survey in the lab, please accomplish it because the way that we're going to go on that, if you fulfill it, that's 100 points in a lab report. So you're going to have, instead of 11, that's the 12 lab report. And of that 12 lab reports, we're going to cancel 2 instead of the one that I originally promised to you. Because we have 11 lab reports. The one that's going to submit is today, the last one. And the other one is the home experiment. That is 15% of your grade. So if you do that, what we call survey, so you have 12 lab reports entry, we just cancel the 2 lowest lab reports. So that's already an automatic 100 by just answering the questions that you have there. Okay. So as I've told you at the beginning, this is new to me because we do the chapter quizzes instead of the long exams. But the main reason for that is the time that we're given to us is really short than the usual time. Usually I have 12 weeks or 12 meetings, but right now we're just given 11 meetings. So it's really hard to do that thing. Even with the 12 meetings before, we have a hard time. So the last meeting that you're going to have, we're not going to meet anymore. I mean, face to face. This is the last time you will see me. uh, On Monday, from between 9 to 12, you have to take your final exam. It is respondus, just like your quizzes. It is made up of 50 to 60 questions that you need to finish within 2 hours. But the window that you have is between 9 to 12. Okay? So, what else do I need to remind you? So the quiz for this will be available tomorrow. And again, you have two attempts to do that. All the quizzes will be uh, closed by Saturday to Sunday midnight. So the transition there between the two. So that I can open it on a Sunday, all the quizzes, questions that you have, see where you're wrong, to prepare you for your final exam. Okay? And if you have not done yet, you can do the student evaluation. I think the deadline, if I'm not mistaken, is today. Okay, so that you will not be what we call delayed in knowing